All right, trigonometric functions. So we're going to go over the derivatives, the derivations. In order to be able to figure out the derivatives and the derivations, we've got to start with the limit definition. For all of these, in order to do the limit definition, we're going to encounter two different limits, both of which are a little bit difficult to explore and require us to kind of have a little bit of a, no pun intended, a little bit of a side tangent before we can get back into being able to do the derivatives of sine and cosine. So we're going to see how far we can get on these. We've explored that we have a number of shortcuts already. Remember, these shortcuts are not reasons. These are just shortcuts. If I say derivative, what is a derivative? It's an approach of slopes. It's the limit definition. We need approach, limit, slopes, the difference quotients. We need the limit of the difference quotient unless we are given permission to use a shortcut. So on the test, be prepared that, like this one in particular, I will ask you for a solution using the limit definition. Count on it. Make it a guarantee. Of which function? Don't know yet, right? But I will be asking you to show me that you understand what a derivative is, and then on other problems will give you permission to use these shortcuts so that you can go through the problems more quickly and derive meaning from the context. So just understand there's a difference between those. So we're going to try to go through all the different trigonometric functions. The nice thing is that we don't have to explore all the different trigonometric functions through the limit definition. We can start with trying to understand sine of x. If we understand sine of x talks about how a function is changing or how the circle is changing vertically, not if we're good with sine of x having to do with the height of triangles or the y component on the unit circle. Give me a general nod if we feel like we remember that. All right, maybe not so much, seeing a little bit less. All right, so let's do a little quick exploration. If I have a unit circle and I make some angle, I call that angle x. That if I want to figure out where this is on the coordinate plane, that is a sine of x height and a cosine of x sideways. So I can make that into a coordinate. See where we get a little bit of difficulty there with that sideways part. Let's make this theta. And now we have sine of theta, cosine of theta, giving us our x's and y's. So our coordinate is cosine of theta, comma, sine of theta. So we're going to have a couple of different moments here where I talk about sine of x. When I'm talking about x in that context, sine of x is talking about sine of an angle. Sine is always trying to turn angle into a ratio, an angle into a height. Cosine is always trying to turn an angle into a ratio, an angle into a sideways. So we've just got this relationship where if I'm talking about sine of something, we're referring to it as an angle. Now give me a general nod if we feel good on the idea that sine is talking about the vertical piece. Okay, excellent. Now, also keep in mind that we're going to be talking about angles in terms of radians. Last time we explored that radians are radius angles. They are angles formed from one radius length. So if I talk about a circle that has a radius, and I take that radius and I stretch it, I kind of bend it around the circle, that length right there, if this is r and that is r, that is 1 radian. So a radian is a radius angle. It's an angle that's formed by stretching the radius along the unit circle, bending it. So that means that if I talk about how many radiuses fit around the entire circle, how many would that be? 6 1/4, about 2 pi to be exact, right? 2 pi radiuses go around the unit circle. How many diameters is that? Pi diameters. That's why one of the formulas we have for circumference is pi times d. Because literally we're saying I have a little bit more than 3 diameters that go around every circle in existence. It's one of the first ways that we identified and defined pi. Pi is the ratio of a circle's circumference to its diameter. Okay, cool. So let's take a look at this one here. We're going to try to trap the segment of the circle, the little pie slice, between the inner triangle and the outer triangle. So let's begin to set that up. area of the segment, that is this curvy pie slice, is going to be less than or equal to, at all times, this large triangle. Now, this large triangle has a height of tangent. Why? Let's come back to that. Let's just say that it's going to be smaller than that area of the triangle, which is OAB, and bigger than the area of this smaller triangle, which I could call OCD. Give me a general nod if we're following, that I can see that that pie slice is bigger than the small triangle and smaller than the bigger triangle. Okay, cool. Then that's how we're going to begin this entire thing. Now, it gives us the answer in this diagram, but let's recognize that this small triangle has a height of sine of x and a length of cosine of x. And that if I scale that thing up, just like by dragging it with PowerPoint here, I can grab this thing and try to make it bigger. I'm going to keep the proportions the same. So since I have another triangle that's on the outside of that, that length is what? 1, because it's on that unit circle, right? Why do we call it a unit circle? Because its radius is 1 unit. So it's a unit circle. It's a radius 1 circle. It's a unit circle. So now we've got, this is going to be the radius. The radius there is 1. If I talk about how big is this thing, how much does it scale up as, I can do a little bit of proportional relationship. I can say with the small triangle, I had sine of x versus cosine of x for my lengths. For this new triangle, I have 1 instead of cosine of x. How big does the numerator have to be to keep this true? It has to be tangent, because I can divide the cosine of x by cosine of x and get the 1. And if I divide the sine of x by cosine of x, I get the tangent. That's the operation through here. It's the division by cosine of x on the top and bottom. So that means that this height right here is 1. Oh, that's what it says right here, right? Or sorry, this height right here is tangent with a length of 1. There we go. That's what this says up here. So let's go through and start making some areas of the triangles and the segments. Equation for the area of a triangle would be 1/2 base times height. We'll start with the small one. The base of the small one is going to be from O to D. That is what? Cosine of x. It says it right here, right? Cosine of x. And then if I talk about from the height of this would be sine of x. Let's come back to the middle. Let's do the bigger triangle. Let me see a hand. Besides you two, because you two are already doing good. Who can walk me through the size of that big triangle? You want to take a step? Go ahead. Yeah. So that's Pythagorean theorem. Pythagorean theorem finds me lengths, does not find me area. How do I find area of a triangle? 1/2 base times height. So I start off with 1/2. What's the base of that triangle? 1. What's the height of that triangle? There you go. What about the segment? Well, if I have a segment and it's measured in radians for its angle, and I know there's 2 pi radians in the whole circle, I could figure out how many radians I have out of 2 pi, and then that would be how much area I have out of the area of the circle. So I'm talking about this right here as being a percentage of the circle's area. Well, the percentage would be how much angle I have versus the full angles, and the circle's area would be pi r squared, where the radius is what? 1. That just means ditto, means I'm going to pull all the rest of this down and do some simplification. So if I cancel away the division by 2's in everywhere by multiplying by 2, I should get cosine of x times sine of x is less than or equal to, the 2 cancels away, the pi's cancel, and 1 squared doesn't mean anything. Which is less than or equal to tangent of x. This is where I'm pausing, because I want to make sure that we are rock solid on how I got here, and that you all have an opportunity to write yourself little notes off to the side. Yeah, go ahead.
Yeah, so I got
which specific part?
like how do you go from having multiplication to 1/2?
Sure, I had 1/2 being multiplied by every single piece of this, right? So I can cancel it across all of those, or you can think of it as let's multiply everything by 2. If you multiply everything by 2, then it cancels the 1/2 in the first piece, the middle piece, and the last piece. Good questions. I like these questions. Everybody else, do we see where everything changed from line to line? If not, this is a good time to ask. Still seeing some people writing and looking at the boards. That tells me we're still figuring it out. Why don't y'all give me some thumbs up when you're good so I can track who all needs some more time. Just keep them up. You can put them on the table if you want to rest your hand, but let's keep them up so I can see them. We got about 4 people, maybe 5 people that I'm still looking for. 3, 2, 1. Okay, feeling pretty good. All right. Let's clean up some of this and start doing some simplification. I need to make this look like the structure I'm trying to squeeze. So I need to get a sine of x relationship here. I can divide everything by sine of x. First, is that allowed? You seem like you're not pretty enthusiastic. Please tell me why it's allowed. So I'm good with the idea that I can divide everything by the same number. This isn't a number, though. What's the only, are we always able to divide by the same thing? What was it? Can't divide by 0. Is this 0? Could be. Ah, there we are, right? So long as I eventually start moving this map towards the idea of approach, I'm good. But at this point, there's nothing in here that says limit, right? So at this point, if you choose to write this like I am with algebra or trig, you need to put off to the side, sine of x can't be 0, right? To be proper in this stage, we need to say I'm allowed to do this so long as I have not created a divide by 0 here. And we'll need to make sure that we keep that true for the rest of our work. Okay, so then if I do a little simplification, we get cosine of x less than or equal to x over sine of x less than or equal to tangent of x divided by sine of x. What's that? Close, not cosine. Secant, right? Tangent is sine over cosine. If I divide that by sine, I'm left with 1 over cosine, or secant. I'm going to leave it as 1 over cosine. I don't usually like to simplify my work into cotangents or cosecants or secants until the very last step, because otherwise I find within myself that I lose context for what it means, right? I don't know if the rest of you are the same way. Maybe you are able to speak very fluently about secant and cosecant, but I am always thinking of them in terms of sines and cosines. So I save that for my simplification at the end, and I keep it in terms of sines and cosines as much as I can. Well, this is almost looking like what I have, but I need to invert everything. What do I do with those inequalities? Let me see a hand from someone I haven't spoken to yet. Yeah, Craig, help me out. So if we're looking at division, let's imagine this right now is a small number. 1 over cosine of x, let's imagine that's small. I'm about to do the reciprocal of it. That means that I'm about to flip it. So now it's 1 over whatever that thing was, right? So if it was small and I do 1 over that, I get big number. Good. What about for the other ones? If it was a big number and I do 1 over that, now it becomes a small number. So it took everything that's small or lesser and made it big or greater. It took everything that was greater or big and made it lesser or small. So what should we do with the inequalities? I like to add some things here where I say, let's imagine this one is the bigger and this one is the smaller. So on the next line down, you said when I do the reciprocal, this one now became the bigger and this one now became the smaller. Do you feel good with that? So what do we do with the inequality? Does it face towards the bigger or to the smaller? Yeah, exactly right, right? We would need to flip the inequality so that it keeps that truth, right? That I'm still recognizing that the bigger thing is now in the middle compared to the right-hand side. So that means that this inequality has flipped. So take that for the next one there, Craig. What should I do with that other inequality? Same thing, right? If I'm still changing big numbers to small numbers and I had a relationship before, I was saying one thing was lesser and the other greater. If I flip that conversation, now the other thing is greater and the first is lesser. So I flip all of these inequalities whenever we do a reciprocal. Let me pause here for a moment, see if anybody has any questions as to why when I do the reciprocal of everything, I flip the directions of the inequalities. Good.
I have a question. Why?
Because right now I'm trying to make it where I'm eventually pursuing the limit of sine of x over x. And what we had was x over sine of x. Super close, just not quite there yet. Yeah, go ahead.
It's the exact same line.
Yep, so it's exactly that. And all we did was we just changed the inequalities so that now it matched up nicely.
Yeah. And, well, if you look at the previous line, it's just written. So the inequalities are the same. Sine of x is still less than.
Yep. Yeah, kind of trapped it between both of those, which is going to be nice and convenient. Yeah.
And we also divide by sine of x.
Yeah, we divided by the sine of x in this line so that we could make it match our pursuit, right? Make it match that structure that we're trying to work with. Okay. I'll help carry us to the end here. I'm going to consider the limit so that it finally matches this full structure. I'm going to do the limit as x goes to 0, and I'm going to do it of everything. So walk this through with me. If x becomes close to 0, what does cosine become? Close to 1, right? By squeeze theorem, what does that say that my middle thing is? What state is? So it's 1, right? I have to be less than or equal to 1, greater than or equal to 1. That means I am 1. So by squeeze theorem, limit as x goes to 0, sine of x over x. Do we feel like we could go explain this proof to somebody after class? That's what I want to understand. Because really what I like, the way that this class is structured, the method that I have in mind for this class is that I want this class not to be a chance for you all to copy down notes, because in all honesty, there's no value in that I see, right? It causes you to have to split your attention to your notebook while I'm talking. That's not helpful. It causes you to have to make sure you capture everything without typo, which you all don't know what we're talking about in fluidity yet, so that's not safe, right? What I want is for you all to be engaged in the understanding of the why during class and go, oh, I understand, like I get that. And then you leave class, you take the guided notes and you write all of your understanding in your words in the margins so that you can tie it into everything we talked about that day, so that when you come back from spring break, you go, I've got the formal, I understand what the formal means and why the formal is important. And then everything is captured. Versus if it's in your notebook, then you're leaving yourself the opportunity for typos and you're leaving yourself the opportunity for split attention and missed details. Like, I don't care if you want to write the notes, but writing notes can be an activity that you do anytime, right? Pursuing understanding is something you can really only do in class because it's the only time we have for us to be able to ask questions and answer them. So that's really where I'm like always pushing on the, does everybody understand and do we have questions? Because whether you wrote it down or not, you can pull up the guided notes and be like, I can add my understanding to these notes and now I have the best of all worlds. Yeah, but
I had a question. I think about the slide.
Previous slide. Previous slide. Previous slide. I got nothing for you.
It was when we first started the problem where halftime based on type.
Yeah, so I erased that to make room for stuff. Okay, when we started off the triangle, inner triangle, outer triangle segment in between. Yes.
Mm-hmm. You know how we did x over 2 pi times?
Yes.
Is that always going to be like that for Trig?
Well, so I don't like words like always. Always are very, very seldomly used words. What I know is that I started off with saying that the segment was a % of the circle's area, right? What percentage? Well, however much I have for my angle versus 100% angle, right? Full circle angle was 2 pi radians. X is a portion of that, so this gets me the %. The circle was pi r squared. So with a little bit of simplification, we said that's x over 2 pi times pi radius squared got us x over 2. Cool? Good. Love the questions. All right, good stuff. Let's take a look at this one. A little less writing. I'm going to go through it quicker. Again, this one is provided for in the guided notes. There's only one trick to being able to simplify this one nicely. Because we don't want to try to tackle this as something brand new if we already have skills available to us. For example, right now, this is talking about a cosine function. I don't want to pursue looking at the limit of a cosine function if I already have knowledge about a sine function, right? And cosine and sine are very closely related. In fact, cosine is the same thing as sine, it's just delayed 90 degrees, right? That's, I mean, literally by the time you get a quarter of the way through the circle, then you're growing sideways in the same way that you used to be growing vertically. Like that's how it causes it to do that nice little arc around. So cosine and sine are the exact same thing. They're just a little bit delayed. If I can make one in terms of the other, now I have a lot less work to do. So we need to try to turn the cosine of x into something about sines. What are some relationships we know between sine and cosine? Let's bring back some of those trigonometric formulas. We can connect them to tangent, but that doesn't allow me to switch between them. It just allows me to create something new. I want to switch between them. Sine squared plus cosine squared equals 1. Do we feel like we could explain to somebody real quick why that's true? Because it's the Pythagorean. Like, look, we just said that we have this triangle, right? Where its height is sine of x, its length is cosine of x, and its radius is, oh, sorry, hypotenuse is 1, because it's the radius, because it's on a circle, right? So we got this ability of saying, oh, it's just Pythagorean theorem of a squared plus b squared equals c squared. And we just grab all that and pull it in. That's why it's called a Pythagorean identity, by the way. So it comes from the Pythagorean theorem. Oh, how do you get the rest of the identities? You divide by sine squared, and then you get the one that's cotangent and cosecant. If you divide by the one that is sine or cosine squared, then you get the one that's tangent and cosecant, right? Like you Want to get the other ones? Divide everything by one or the other. That's the other one. And then there's a third one if you choose to divide by cosine squared instead. Right? Like you don't have to memorize these. They're things you already know. They're things you can prove very easily. All right, anyway, so we want to try to make this look something like the Pythagorean identity. I've got a cosine of x minus 1. I need to make that a squared and keep it as a minus. That sounds like maybe a multiplying by conjugate type strategy. So let's go ahead and work that through. We're going to multiply by the conjugate. We'll multiply by cosine of x plus 1. It's a good way to make the top thing squared without introducing middle terms. And I can't square it directly because that changes the meaning. So I'll multiply by the conjugate. That gets me the Pythagorean identity on the top. Replace the Pythagorean identity with sine of x. And we're already off to the races. Like I said, I don't have a lot of time in the lecture for us to be able to copy it down, but thankfully it is all written out, I think, in the guided notes. Or there's a nice space for it, so long as we remember that there's really only one trick in the beginning, and that's multiplying by the conjugate. Do we feel good on how I was able to go from the original thing to this thing so far? Do y'all see that I have a sine of x over x piece in there? Right, I can kind of maybe do a little bit of rearranging and I get a sine of x over x piece. That's the limit we just proved on the last slide. So if I do a little bit of algebraic manipulations here, I can use what we discovered earlier. Let's separate it out blatantly. As x comes in towards 0, what's that first parenthesis going to turn into? It's going to turn into 1. That's what we found out on the previous side. Even if we don't have that one memorized, let's go back to that picture. That picture is super useful. If I look at a segment compared to that sine amount, as I bring that angle in, do we see that the circle's arc starts to be more and more vertical? Like, here's what I mean by that. Let's bring it in. So now I'm looking at this piece right here. So I've got a vertical and I've got an arc. Do we see how that piece of arc is much more vertical than the bigger one? And if I bring it in more, I get more vertical arc, more verticalness to the arc, more verticalness to the arc, more verticalness to the arc. So what's the ratio of forever more vertical against vertical? What's the ratio of two similar things? Like 5 over 5 or 10 over 10. It comes out to 1. That's where we're getting this from, right? As we bring the angle in, the circle becomes vertical, and the ratio of the circle's verticalness to literal verticalness is 1 to 1, or 1. So the first thing's going to come out to be 1. What's the other thing going to come out to be? As x becomes really small, sine of x becomes as x becomes small, sine of x becomes closer to sine of 0. Sine of 0 would be 0, right? Sine of 0 is 0 because I'm up nothing there. So the top becomes 0. What about cosine of 0? That becomes 1. So I'm going to get 0 over 1 plus 1. 0 over 1 plus 1 is 0 over 2, which is 0, right? First thing becomes 1 because we proved it on the last slide. Second thing becomes 0 because there's no barriers. I can just evaluate that one. So I get 0. So we've now got our two component pieces to begin working through some of our derivatives. Again, it's not about having this memorized. It's not about having this written. Y'all have a book you can purchase for the class if you want. It's got everything written, right? Y'all have the guided notes. It's got everything written. Heck, you've got a recording that I'm making right now. Everything's written, right? It's about feeling like if you saw this proof on paper, you could explain it. That's what we're trying to do. We're trying to pursue understanding, not try to capture proofs. So that's really why I keep checking in. Do we feel like we could explain what happened here and why it was logical? And so before we start exploring the derivative of sine of x and cosine of x, it's worth noting that like we have this connection that says sine of x and cosine of x are related, they're just delayed. In fact, with the graph, we get to see that quite clearly, right? If I look right here at sine of x, and I draw a tangent line, what's the derivative of sine of x there? 0, right? Somebody else tell me why that makes sense. There we go. As we consider the approach of slopes supports 0, right? You could either say that, or you could say the slope of the tangent line, right? You got to specify that specifically for that tangent line, not for the equation. Because we're going to grab a couple of slopes this way. Let's grab a slope that's shallow and more shallow and more shallow. And from the left, it looks like it's going to become forever shallow. And from the other direction, I grab an approach of slopes. I make an approach of slope, 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 and it becomes forever shallow. Forever shallow is 0. We have a slope of 0 for that tangent line. Any of those are good stories, right? Notice, what's the cosine value right below it? No, that's the x value. What's the cosine value? What's the height of the cosine graph? 0. That's kind of nice. When the tangent line was a slope of 0, the cosine graph also had a height of 0. Let's go exploring. What about right here? Here, the sine graph has a tangent line with a slope just about, looks like, I don't know, something positive-ish. What's the cosine values height there? +1. That seems nice and correlated. In fact, let's go over here. Here, I've got another tangent line with a 0 slope. The cosine value is 0 at that same x value. We've got a little bit of a connection here, maybe. It seems like the height of the cosine graph, in other words, the cosine's value, matches the derivative for sine. Have we proven that formally yet? No. But in actuality, this is the case. And so now we've just got to prove it formally. So again, I've got this thing all up here and written. We always start a formal proof by going back to the limit definition. That's what it is. That's what a derivative is. So we've got sine of x that we're considering. We can plug x plus h into it. We can plug x into it. We can set it all up with that difference quotient because we're looking at the approach of slopes. Well, what do we've got sine of x plus h. That looks like another trig formula, right? What trig formula would that be? Like, I don't need the memorization of it, but just like what remember what it's called, or we know x is an angle, right? And h is a little further of an angle. So I've got a sum of angles. Oh, sum of angles. We have a formula for sine with sum of angles, right? Maybe we've seen that in textbooks where it was sine of a plus b. Something like that. We can use that here, and we can change the appearance. There's a lot of nasty, scary, hairy things going on in here, but if you look at it closely, we start to see those two little pieces of mise en place that we brought in earlier. Do we all see that on the bottom I've got an h, and on the top I have a bunch of sine of h's? Like, I got an h on the bottom, I got a couple sine h's on the top, and h is going towards 0. That's the formula that we had proved earlier. So we're going to try to make that explicit. We're going to group and factor so that we start to make apparent those two formulas that we had. Notice here I've got that cosine of h minus 1 over h that's starting to appear. And on the other one, I've got sine of h over h that's starting to appear. I've got the two pieces for the mise en place. I can separate those and start to make that look more and more accurate. Since the limit is approaching 0 for both, I can have the limit approach 0 for both. That looks fine. As h gets small, does sine of x change? I don't see an h anywhere in that, right? If h gets small, sine of x is still its own thing. As h gets small and I make it 0.1, I don't plug in 0.1 for x, I plug it in for h. So this doesn't change as my limit gets small. I can pull it out front. In fact, this one doesn't change as h gets small. I can pull it out front. And then these two pieces are exactly what we explored. That's the formula for the first one. That's the formula for the second one. And we get that it's cosine of x. I'm going to leave this one up here just so we can have a chance to kind of discuss it on your way out. We still need to prove a couple of the other pieces from later. But again, double check before you leave that you don't have any questions to be able to capture in your notebook when you go back and try to formally write your notes. The idea is that all this should feel approachable. It just should be new. That's totally fine. All right, y'all are good to go. If you have any questions, let me know. Cosine of x equals negative sine of x. Maybe we'll try this one together. It's looking like we might have the time for it. If I want to look at a derivative formally, I start with the limit definition. That'll give me the derivative at x when I approach x by bringing that gap in smaller. If I want to explore it for cosine of x, that just means that I'm plugging in all the storyline to cosine of x specifically. So instead of it being x and a little later for a function, it's x and a little later for cosine. Instead of it being minus some height earlier, it's minus some cosine value earlier. At this point, what would we want to consider if we're mirroring that similar proof? Yeah, with sum of angles for cosine, right? I forget always what the one for that is. Get cosines and then subtracting of sines. I can prove it, but it always escapes my memory. I told you, I'm not awesome with memorizing it. It would take me less time to reprove it than it would for me to try to memorize it. I will probably provide those. And if not, I will specifically tell you which ones to memorize. What are we seeing here that we recognize that we can work with? What is he? We're seeing cosine of what? Cosine of h or cosine of x? You know what to do with cosine of x? See a couple of them, maybe group them together just factoring? Let's try it. That would be leaving behind a cosine of h and leaving behind a -1. And then we haven't touched that negative sine of x, sine of h, all over h. What do we see that we recognize? You make it two different ones. We can do that. Yeah, go ahead. What do you see?
Take out this cosine on the side.
What do you mean take out what cosine and sine?
That's the side of it.
We could take those out, sure. Or, I mean, really, that's just a way of us trying to visually show that, like, that's not changing. The other things are changing, right?
Yeah.
How are the other things changing? Like, I got cosine of h minus 1 over h as h goes to 0. How's that changing? Like in this first fraction, I've got this over this looks like one of the limits we explored, right? That one turns into 0. And leaves behind that cosine of x. Cosine of x doesn't change. That latter part ratios out to 0. What about this next one? Yeah, that sine of h over h goes to 1, because remember, sine of h talks about the vertical, and h talks about the arc size. If the arc size and the vertical start to match each other closer and closer as I get those smaller angles, that means that comes out to 1. So I've got, that's sine of x, and then the sine of h over h goes to 1, so we have this simplified to negative sine of x. Let's double check. If I go back to my circle, what's the sine value here at the top? 1. How is cosine changing? It's towards the, it's towards the left, right? If I'm going to draw this picture in the direction that I grow my angle, then at that moment I'm drawing it entirely that way, which is towards the negative. I'm changing cosine negatively completely, right? All of my change is going towards cosine negatively. So that's why at that value, I use the 1 from sine, but it's a negative change, right? It's the negative relationship of saying that if sine is complete, cosine is about to change negatively. If sine is negatively complete, cosine is about to change positively. If sine is, no, sorry, if cosine is -1, sine is about to change negatively. And if sine is 0, which again is still over here, cosine is about to change positively, right? So you've got this play that happens between the derivative of sine being cosine and the derivative of cosine being negative sine. Well, in fact, that actually helps us out quite a bit, because then if I asked, what is the derivative of negative sine of x? Yeah, how come? You can make it from the storyline. I like the storyline. We could also do it from mechanics, right? Isn't this the same thing as -1 times sine? And isn't that the idea of saying a constant times something that changes is just that constant times that thing's change, which is that constant times that thing's derivative? Like I can think of this as -1 times the derivative of positive sine, which we already established is -1 times cosine of x. So the derivative of negative sine of x must be negative cosine of x. What's the derivative of negative cosine of x? It'd be negative of the derivative of positive cosine, right? And the derivative of positive cosine, we said, is negative sine of x. So we've got the negative of negative sine of x, that's positive sine of x. Oh my gosh, we've got kind of like this big rotational symmetry that makes total sense with the fact that we're talking about drawing circles that are rotational, right? So we've got this beautiful cyclical nature to these derivatives, where the derivative of sine of x is cosine of x, the derivative of cosine of x is negative sine of x, the derivative of negative sine of x is negative cosine of x, the derivative of negative cosine of x is back to positive sine of x, and we continue to loop on through because everything is delayed 90 degrees, and by the time you consider 4 90 degrees delays, you're back to the beginning. We have not used this notation very much, but every once in a while it comes up. As a reminder, this is a way of saying what is the 31st derivative, right? So instead of putting 31 little primes, is a way of saying 31st derivative. If I say that f of x is sine of x, what's the 31st derivative? Okay. Yeah, exactly right, right? 32 would be some amount of 4 repetitions, right? And every 4 repetitions, I'm back to a baseline. So we could trace this all out if we wanted. We could say this is going to be the same thing as the 27th derivative, right? 4 earlier would have been the exact same thing. And that would be the same thing as the 23rd, the 19th, the 15th, the 11th, the 7th, the 3rd. The 3rd derivative. Oh, well, the 3rd derivative gets us to negative cosine x. Let's do a proof for another. What about tangent of x? Well, as we already mentioned, we don't need to have this memorized. In fact, I almost never have these memorized, and I've been doing this for years. So if y'all are better at memorizing than I am, have at. I'm learning to get better at memorizing, right? That's why I'm doing pretty good with people's names this semester. But overall, it's a skill set that like I do not have by default. So it's always been easier for me to derive these off to the side of an exam if I forget or have extra time than to try to remember them, especially with the other amounts of stuff that you have in the class. So let's just talk about how we would derive this. Instead of tangent of x, I almost never think of tangent of x as its own thing. I always think of it in terms of sine of x and cosine of x, right? So let's just explore that. If I wanted to consider this derivative, we could go at it formally through the limit definition. But unless we are specifically being asked for that, there's absolutely no need. We've already established shortcuts that assist, right? And since here, my component functions I already have derivatives for, I just need to think about what's the operations between them. Like what rule or shortcut would we use here? We use quotient rule. So let's save ourselves some heartache. Let's do a little mise en place off to the side, right? Make sure we're not getting a little overwhelmed. So we could call one of these f. F might be sine of x. We could call one of these g, cosine of x. F prime of x would be then what? Cosine. And g prime would be negative sine of x. So then I go through my little limerick, right? We've got quotient rule is low d high minus high d low, all over denominator squared we go. Eventually, you'd want to kind of get to where you can do that in real time with less and less mise en place, but there's absolutely no harm in doing it to begin, right? So we could do low d high minus high d low. I like to maybe make that a little more explicit, right? We call the top thing f, we call the bottom thing g. So low d high minus high d low, all over denominator squared we go. And so then we just grab and we pull in. Cosine of x times f prime, which would be cosine of x, minus f, which is sine of x, g prime, which is negative sine of x, all over g squared, which would be cosine of x squared, or cosine squared of x, I should say. Looks like a lot. It's going to simplify real quick. Top becomes cosine squared of x. So sine squared of x over cosine squared of x. Cosine squared of x plus sine squared of x is 1. It's a Pythagorean identity. It goes back to that exact same Pythagorean theorem with the triangles that we did at the beginning of the lesson. So this is 1. And 1 over cosine squared of x we could rewrite as secant squared of x. So we've got some time. Let's go ahead and get into our groups. I would like y'all to try, as far as you can get into the list, of proving some of these other ones. So we've already proven the derivative of sine, derivative of cosine. We've now done the derivative of tangent. See if, with your group mates, you can derive the rest. You don't need to use the limit definition. We have shortcuts for it. But my recommendation is think of everything in terms of sines and cosines and work from there. So why don't we go into our areas for our groups and give those a shot.